Okay, share my pad. Oops. All right, let me see what's going on here. Sharing pad. Ready? Zoom. Great. Okay. So let me draw the problem out. Let me draw the problem out. Okay. So the problem looks like this. The problem looks like this. I have a frame. So the frame has a beam on top. Okay. Frame has a beam on top. I have a support column here. Flush, by the way, flush here. Okay. And it was fixed on the ground here. Another column fixed on the ground here. Okay. And I say the column has a width of 12 inches and the whole length of the beam, from center to center, okay? This is from center to center. From center to center, okay? This is 19 feet. This is 19 feet, all right? And now the inside clear span of the column is 18 feet, okay? Half foot from left, half foot from the right, okay? And applied load here, okay, applied load here, omega u is 9 kips per linear foot, 9 kips per linear foot, okay? So the problem says the beam shown below has this large load, okay? And it's going to determine VU, so VU at, okay, at what? At the center line of support, okay, at the face of support, okay, at critical sections, and at midspan. Okay, so we need to determine VU for all these critical sections. Okay, so first of all, let's draw the shear diagram, shall we? Let's draw the shear diagram. So now, if I want to draw the shear diagram, I need to know where the support at. Okay, so when I assume a simply supported condition, what actually I have, let me use a blue line here. Okay, it from center line, extending out from center line here, and this is the support. Okay. This is the support. So the simplified beam, okay? Let me put it here so I can see it better. So the center line gives me a simply supported beam and simplified drawing here as that. So this is my reaction force, and this is my reaction force. Okay, so the shear diagram is gonna look like this. Triangle, okay? And as you know, 0 in the middle, so I'm going to draw the straight line here as that, okay? Straight line here as that, okay? All right, so now I have to find out my VU max at end, okay? So what is VU max? VU max, so stop. VU max, in this case, is no more than omega UL divided by 2. Omega UL divided by 2. Now you will know that omega U is 9 kips per linear foot. Okay. Now the span length, though, in this case is 19. Okay, is 19 foot. 19 foot. All right. So here VU max. This is where. This is at center line of support. This is at center line of support. Okay, so this is at center line of support. All right, now if I trace along the shear diagram, I say the face of support. Where is the face of support? It's right here. Right here. Okay, and the distance between the Vmax to the face of support is what? 6 inches. 6 inches. Okay, so I just need to go down the linear line to reach the 6 inches, okay, to find out the shear. So how do we find that? How do we find that? It's simple, right? So I don't know this. So let's say VU at face of support. So VU at face, okay? So VU here, face of support here, divided by what? Divided by this length, okay? Divided by what? This is what? This is half of L minus 6 inches. So half of L minus. Questions? Any questions? So 0.5 feet. Okay, 6 inches, 0.5 feet. Okay. So if you have a question, you can feel free to interrupt or send me a chat message. Okay, send me a chat message. Okay, either way. Okay. All right. So that VU face divided by that should equal to what? Should equal to VU max divided by half L. Similarities, right? Triangular similar trigonometries, right? And from that, I can find out the VU at support. VU at say face support. So VU at face should equal to VU max. Okay, divided by half L multiplied by half L minus half feet. So that's that for the shear and face of support. Now, looking back, right? Looking back, the problem is also asking what? At the critical section, at the critical section, right? At the critical section. Where is this critical section? Where is the critical section? I'm going to use red here to differentiate, okay? So same diagram, okay? Same diagram. So what I'm going to do, I'm going to copy this. I'm going to redraw the shear diagram, okay? Redraw the shear diagram, okay? So this is the maximum shear. This is maximum shear. Okay, hold on. I got somebody on the line. Okay, here we go, buddy. All right, so if you have a question, feel free to shout out or send me a message, okay? All right, now I have the shear diagram, right? I just copy it down. I didn't do anything else but copy it down, okay? So this is basically 19 feet, all right? 19 feet, okay? Where the critical section is at, that's the question, right? Where the critical section is at. Now, be careful. So I'm gonna use red here. This is at the center line of support. So center line support. And 6 inches away from it, 6 inches away from it. This is at the face of support. This is at the face of support. Now, critical section is what? Critical section is D away from the face of support. From the face of support. Okay, D away from the face of support. So you need to know D. You need to know the depths. You need to know the depths. Okay, so looking back, actually the problem provided you the D. How so? Because there is a joint from the T section showing here. So this is the T section for the beam. Okay, and now the width of the beam is flange width 36 inches, right? And the web is 12 inches, okay? Those are fine. And the depth is from the top fiber to the reinforcement, right? And that D equal to 21.5 inch. That is 21.5 inch. So this here, D is 21.5 inch, okay? Now, when I do that, okay, I still want to find out, right? So per se, now this value here should be VU at the critical section. So VU critical. So how to calculate that? VU critical at critical, okay, divided by L over 2, that's 19 feet, right? 19 feet divided by 2 minus 0.5 feet, that gets you the face of support. That gets you to the face of support minus a D. Minus a D, okay? And now that equal to VU max divided by half of L, okay? Okay, so now you can compute the shear force at a critical section. Okay, all right. Now, also asking you what is the shear force at midspan? So at midspan right here. So VU at midspan equal to 0. Right? No shear. Okay. All right. So that's problem number 1, right? A. Problem number 1A. B. Okay. What is problem B? Using ACI equation. Well, this should be 19 now, but the equation numbers stay the same. Okay. There's a typo. Sorry about that. Calculate the values for FVC and 0.5 FVC and locate these values on the factor shear force diagram. Okay. So step by step, right? What is FVC? FVC and half FVC, okay? So FVC is what? 2 lambda square root F prime C BWD. So the only trick is BW, right? So for T-beam, this is the BW. Okay, so half of that, well, you can find it. But what is phi? Phi in this case is 0.75, right? Strength reduction factor for shear, constant 0.75. All right, and now once you locate this, right? Once you have these, you need to locate them, right? So again, let's coming back to this shear diagram plot. Okay, I'm going to repeat that again. So since I only care about half of the span, so I'm going to draw it big. Okay. So this is half of the shear diagram. Of course, now the length of it is 19 feet divided by 2. 19 feet divided by 2. And VU max right here is right here, okay? Right here. All right. So all you need to do, how to trace them? All you need to do is this. So asking you to find FVC. So for example, if I already have FVC, okay? So say I have FVC right here. Half of it. Okay, so how do I find this distance x1 here and x2 here? Okay, so in the note, all right, what I did in the note is I'm going to let the x-axis start from left. X-axis start from left. Okay, but you can actually do this. You can do the other way. It's actually easier, right? It's actually easier to do the other way. Okay, from the right. Okay, so I'm going to use this angle here, theta. Okay, and I will say that tangent theta equal to half of FVC divided by x2 equal to FVC divided by x1 and equal to V max divided by 19 feet over 2. Okay, so if you know FVC, half FVC, and you can actually find out x1, x2. Isn't it? All right, so that's the trick here. So you find out x1, x2. Find out x1, x2, okay? So that's problem number 2B, okay? Problem number 3, C, okay? Design the shear reinforcement using number 4, two-leg stirrups. Number 4, two-leg stirrups. Showing the cross-section, at least 2 different regions, use at least 2 different regions stirrup spacing in the design, and provide a sketch of the layout shear reinforcement along the length of the beam. Okay. All right. So think about it, right? So how are we going to design for it? Again, let me put this figure here. So I'm going to copy it. Quite lazy, so I'm going to copy it. Copy and paste. Okay. So let me show you how we're going to do this, right? How we're going to design this. Now, following the equation here, right? Following the equation here. So recall, right? There are three categories. There are three categories, right? So the spacing category, right? So for example, we know that category 2, category 1, so I say cat 1 is VU is lower than half of VBC. In this case, what we say, no stirrups. Absolutely no stirrups. No stirrups, right? So what does that mean? It means here, from this case, I have what? I have no stirrups requirement. All right. You wonder where that's coming from, right? You can go back to our original notes, right? Go back to our original notes, okay? So when we use smaller than half VBC, no stirrups. I'm going to use red. Let me use a division line here. So, sorry. Okay, so here's a division line. So here, no stirrups. No stirrups. Okay, no stirrups. Okay, category 2, category 2. So half of VBC smaller than VU, smaller than VBC. So that means minimum stirrups needed. But recall, let me go back and recall this fellow, where is it at? Right here. Recall this equation right here. This is category 2, right? This is category 2, right? Recall this fellow right here. Okay, this is the spacing requirement. This is the spacing requirement. Is that right? These are still spacing requirements. So I'm going to go back and say, okay, now for this case, as spacing should be least of, required spacing should be smaller or equal than least of D divided by 2, 24, AVFYT 0.75 square root F prime C BW, AVFYT divided by 50 BW. Okay, that is the requirements for spacing. That is the requirement for spacing, right? And now for category 3, okay, but before I go on, right? So I'm gonna label, so this is category 1. Okay, category 1, okay? So for category 2, where is category 2? This is category 2, okay? Category 2, okay? Now, where is category 3, right? So category 3, it says if VU, of course, is bigger than VBC, but smaller than phi for lambda square root of prime C BW, right? BW is a D here. Okay, so in that case, right? In that case, going back, see this case right here, right? So this is the case right here. Okay, VS is smaller than that, right? VS is smaller than that, right? So in this case, right? In this case, sorry, let me go back. These are accidentally. So this is now VU. Let me clarify. This is VU minus VBC, okay? This is VS, all right? VS, okay? So when that happens, this is category 3, category 3. And in response for category 3, S equal to what? List of D over 2, 24 inches, okay? AVFYT 0.75 square root of prime C BW, AVFYT 50 BW. And don't forget, right? Recall, right? Don't forget this, right? The calculated spacing right here, right? Right? So AVFYT, VVA, VYT, VS. okay, and D. Okay, so that is all the spacing requirement you need for category 3. So where is category 3? Category 3 actually should be somewhere here. So this is 4 square root FR1 CBWD. Okay, should be somewhere. Well, this should be the plus VBC. Okay, so it should be somewhere here. Okay, should be somewhere here. And now, where is category 4? Category 4. Category 4 should be Vs is smaller than A square root FRMC BWD. Okay, and bigger than 4. Okay, so that gave me the spacing list of all the other remains, right? All the other remains. Instead, this divided by 4, and this is 12 inches, blah, 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 like before. Okay, like before. Okay, now, so category 4 put us right here, supposedly. Okay, so you see, as my shear force increases, I'm going to go through the whole 4 categories. I'm just going to go through the whole 4 categories. Now the question is, so Bob, last time when you showed design, you only showed 2 different spacing. How come? Right? So why 4 regions, but only 2 spacing? Doesn't make sense. Right? No, it actually makes sense. How? Because if you look, right? If you look, and you know there's a lot of overlapping spacing requirements. For instance, this D over 2 happens here, 24 happens here, these 2 happens here. Okay, and again, if you observe for category 3 and 4, the rest of 3 repeating here again. All right, so normally what you really will find out is that one of these four will govern. One of the 4 will govern. Most cases actually either this one, D over 2, okay, or the 24 inches. So that means I may have the same spacing requirement for all these categories, okay, or all these 2 categories. Okay, so that means I can provide 2 sterile spacing. So normally, let me try to clean up this too, okay? So normally, let me use different color, you can see it. Normally, you can design 2 spacing. Okay, so this is, I call it spacing 1 region, and this is spacing 2 region. Okay, this is what you will end up with. And here, no stirrups. Okay, no stirrups. All right, got it? So we will see all the 4 categories, but when design, we do not necessarily have to design all 4 of them. We do not have to design all 4 of them. Okay, so we might be able to get away with a constant spacing in this category 2, and another spacing in 3 and 4 altogether. 3 and 4 altogether. All right. In exam, right? The critical question in exam, some may say, okay, so should I just provide you the calculation for the 4 design? No, you cannot. You need to show us the full work of 4 categories. And then you show the rationale of picking 2 spacings in this shear design. Okay, in homework and exam, you will show the full work of the 4 categories, okay, and then provide the reason behind the 2 spacing selections based on these 4 categories. All right, okay, now I hope this is clear. And I hope you understand better compared to the notes. So my suggestion is to do this homework right. Please go back to your lecture notes we did last time, and then go over what we have gone through today, okay? Okay, Now notice I only record this part of it for the homework because the exam announcement is not part of the lecture. Okay, but let me say this again here again. Okay, I will make an announcement about the following midterm real quick after we're done with our one-way slab this week, which is probably going to be Wednesday. And then we will schedule the time and the method of delivery for that exam. All right. Okay, before I close out, any burning questions? Any questions? You can voice your question or type the message right now. Any questions on this?
Could you go back down to where the category 4 is real quick?
Sure. So one at a time, Sean, this is category 4. And I heard a voice in their lecture on Thursday. Most likely, yes, because we need to catch up on the one-way slab. Okay, and I will send you the link. And I will repeat this on Tuesday, tomorrow. Okay. Any other questions? I just heard a voice shouting in the background. Can you say that again or type the message again, please? Any other questions? Okay. Are we good? We good? Any other questions? All right. So Tuesday, tomorrow, same time, or actually not same time, but 2 o'clock, right? 2 o'clock. Let me make sure that's the calendar. So I have set it at this calendar. Tuesday, 2 o'clock. 2 to 3, right? 2 to 3, okay? Is our office hour. So 2 o'clock. It's gonna be a short, okay? It's gonna be a short, so I'm gonna make a note here. Office hour. Please bring all your questions regarding homework and exams, okay? Regarding homework and exams, okay? And we'll discuss more on Wednesday on the one-way slab, okay? All right. Sean, are you good here? You need more to show? You need me to show more?
Could you scroll down just a little bit, please?
Sure, right here.
Oh yeah, I mean, wasn't there something? Oh yeah, there you go.
Okay. All right. So I'm just trying to show that category 3 and 4 have a lot of overlapping. Okay, have a lot of overlapping. All right. Okay. Any other questions for me?
The category 3 and 4 are the least of cases. Are those exactly the same?
Yeah. No, only the top 2 is different, right? So the first one become D over 4, so halved. The 24 become 12 inches, half. The other 3 remain the same. Got it?
Oh, yeah, thank you.
Okay, sure. Any other questions? Any other questions? Let me say this again. Any other questions? Okay, so let me repeat this, okay? Shear is one of the most, if not the most, designed for concrete, okay? For reinforced concrete structures, okay? So in your life, you meet basically these critical elements, right? You will do the flexure design, you do the shear design, and you do the column design. So you basically can do beam and column. And we'll provide some detailing information about the joint sections later in the lectures, in the courses, okay? So hopefully you're happy with the information, okay? So let me know if you need more, or else we'll see you tomorrow at 2 o'clock, okay? 2 o'clock in the afternoon. All right, thank you. This is it for today. See you tomorrow.